Welcome to ECE 442-542. This is digital control in the Electrical and Computer Engineering department. This is how I will begin most classes, if not all classes, except the classes that have the exams. I'll have the announcements posted or hopefully viewable when you come in, and you'll see maybe some or all of the goals that we are hoping to accomplish that day. You do have a few assignments that are already scheduled. One of those is your passport. That's your way into this class. We'll talk about that now. You simply answer a few questions, give me a photo so that I can put you with a name. If you go by a nickname, put that down, and then there's some reading that you have to go to a website and read through some chapter summaries. Respond to those chapter summaries in section 4 of your passport and then sign it. And you need to read the code of conduct before you sign it. But that should be fairly self-explanatory. The passport is on the website. Again, an up-to-date photo, your name, your email address, something that is unique to you that I can maybe associate with you. And then here is the information about the chapter summaries I'm wanting you to read. So you don't have to read the entire text, just some chapter summaries. So one paragraph on each chapter, 8 paragraphs. They're quick reads. It's on learning or how we learn, and we'll try to make this stick, the content in this class, which that book is concerned with how we learn as an individual, and that's what I want you to start looking at or thinking about. You'll read those 8 summaries and then respond to those 2 items. One is which of the chapter summaries sort of touched you when you read it. Maybe it makes more sense to you than the others. And then why did you pick that chapter? That's in your passport. If we go back to the class announcements, I've already pre-populated material on D2L. There's 2 sections before we even get started, or 2 units. One unit is the PR. That's not public relations. That's prerequisites and review. You could look at that material and see if that looks very familiar to you. That's fine. But I figure we have a week until we meet again. You have time to watch and look at some previous notes or material that I've provided on state space representation, Laplace transforms, Bode plots, etc., just to get you up to speed with where I think you should maybe be prerequisite and review-wise for this class. That's the PR unit. The 0 unit is really just going to contain the syllabus and the passport and some readings on control, introduction to control, maybe some chapters or different locations in that sense. We've already, before we even made it online, we talked about class attendance and you signing that. If you're a remote student, obviously I will touch base with you at a distance. You don't have to fly to Tucson to sign in one of those particular attachments. Let's now talk about the syllabus, which is the next thing on our goal sheet, or our list of goals. The office hours I haven't yet determined. It's depending on what other people need me to do this semester. Stay tuned. I'll figure out when those can possibly be. I'm guessing maybe Thursday between 3 and 6:30 might not be a good time because many of you are seniors taking the capstone. I will try to avoid that time window. The other thing is maybe I'll have them on Friday if the assignments are due on Friday. That's what I'm thinking. If you think I should be considering other options for office hours, we'll probably have them on Wednesday, maybe Thursday or Friday. I haven't yet decided. But I'm right now tentatively thinking most of our assignments will be due on Friday. There is no textbook for this class, no official textbook, but there are many different resources available, some just on control and some on digital control. But the one that you could maybe go out and buy could be a Shams outline. But that's also available through the library at the University of Arizona as an ebook. So you wouldn't have to purchase anything. You could read the sections through the library's material. It's not a download that I'm aware of. I'm sure there's an illegal download for that Shams outline, but you can read it page by page from the library website. But some ebooks are downloadable. I don't believe this one is. This one you can click through and read online. But we will try to give you the material that you need. If there's background material, it may be on you to find a source that you like and read from that source. And I might suggest or make suggestions as we go. This might be a good chapter or section of this particular book that you might want to look at or read to learn about the material that we're talking about at that point in the semester. But there is no official textbook, and the Shams outline shouldn't be that expensive. I think it should be less than $20 if you went and bought one. And that covers analog and digital. We are focusing on the digital aspect of the material. But a lot of times it's nice to sort of know where we're coming from or what you could have done prior to this. Many of you have taken the automatic control class, which is the analog version sort of this class, and we'll emphasize the digital piece of the control. There will be 3 exams, some homeworks yet to be determined how many, but the breakdown of points and those dates hopefully we will be able to live with. They are probably all on Wednesday, those exam dates, except for the final exam. The final exam is the last day of finals on May 14th, and the final will be earlier in the day. It will be at 1 to 3, and it will also be in this room. The nice thing about this room is you'll be able to spread out on an exam day. We may sit every other seat or every third seat or something so that you have space to work, is the idea. Content-wise, and there's other sections here in terms of what you can read, and that's one of the questions you need to answer on the passport. Have you read the syllabus and the code of conduct, code of academic conduct? That you would then have to sign off on. Here is a collapsed version of the content for the course. We'll start with some modeling, then we will get into block diagrams, some system identification. How do you identify a digital system? And you can do that from a step response, from parameterized model, from the frequency response, etc. Then how do you pick? This is one thing you have to have that you didn't have to have in an analog version of this class. You need to know how fast am I sampling. And that's actually, we'll just talk about a rule of thumb, and that will be pretty easy to know, but it's nice to understand some of the trade-offs and consequences of why you're selecting the sampling rate that you're selecting. But just to get you started, you might just keep 30 in mind. 30 times the closed loop bandwidth is not a bad sampling rate. That's our rule of thumb. So if you know what your closed loop bandwidth is, you sample at a frequency 30 times that, then your sample period is 1 over the frequency in hertz. You now have your sampling period. And if somebody's programming that on some processor, you can tell them, oh, just sample at 30 times the closed loop bandwidth. And they'll look at you like, what's the closed loop bandwidth? And you'll say, oh, that's right, I'm the control person. I'll tell you what that is. So you may be able to guide them through that process. Maybe they are doing the coding of that, and you are telling them what you want them to code in terms of the algorithm. And that's what we will learn in this class, is how do we design these algorithms, which could just be a difference equation. How do we build these difference equations to make this machine, this system, this plant perform the way we want it to perform? That's really the ultimate goal of this class. We've talked about the syllabus. We've talked about some of the course resources. A lot of those are listed on the D2L site under the title, Course Resources, which is near the top of the content page as one of the modules. We've talked about the passport. We will go now through a little bit of a discussion, a quick discussion of why we might be interested in digital control. And then we'll start with the first piece of the class, which is system modeling. That's the plan for today. And today we go until 9 o'clock. It's a short time today. I hope you're ready. Happy New Year. Actually, we have another hour, don't we? I believe. I didn't even know where the clock was, so now at least you know that I know where the clock is. And since the lights are up, maybe I can continue to see that. And if it gets a little late, if it gets close to 8:30, you might start pointing towards the clock. Okay? But anything before 8:30, keep your hands and eyes concentrating on the material. Okay? All right, let's start by looking at why we might be interested in digital control. A lot of this is going to be via block diagrams that we're going to be playing with, and so we might as well get started in that routine. For some of you, this is going to look very familiar, I hope, from those that have just finished the analog version of this class. And I'm putting some different letters down, but R of S, lowercase r of S, it could be a capital case R of S. The S is the frequency domain Laplace variable. R of S is a reference input. D of S is our controller. G of S is our plant or system. That could be the open loop system. The whole thing could be our closed loop system. The whole thing with the plant, the controller, and let me just go ahead and make it unity feedback, meaning I don't have anything, any operation or any kind of filter or control or sensor dynamics in the feedback path, and I'm comparing now this reference signal to the output Y of S. That then generates or creates an error signal, and this now, everything is in the variable S, which really means this is an analog control system. This is coming to you, maybe it's given to you, maybe it's what you've done in a previous class, or it may just be, this is a example that I now want to talk about. And coming out of a class, whether that's analog or digital, a lot of times you're focused on how do I build that controller. From an analog perspective, that D of S may have some issues. And so we're trying to answer that question, why digital control? D of S, as a transfer function or as a subsystem, it may be susceptible to many different things. Maybe it's susceptible to the environment. or environmental conditions. Where there you might think temperature, humidity, etc. Or it may be susceptible, or it could be susceptible to the aging of different components. Maybe you've built that with op amps, resistors, capacitors. That's what's sitting in this D of S box. Maybe those are now aging. Or maybe you were building this on the cheap and you couldn't specify everything to 0.05% tolerance. And now you have this sort of sloppy D of S that you've designed. And so D of S is susceptible to these tolerances. You might have noise that D of S is susceptible to, and or in that D of S you may have parameters that might drift with time or something else. With environmental conditions, those parameters might be expensive, meaning all of those pieces and parts might be expensive to purchase and build and construct to build that controller, or they may even be unreliable. Those are some possible concerns you might have with this D of S that's now just a transfer function that's implementing some algorithm or some control law that helps stabilize or achieve what you want in the closed loop system. We don't really need to worry so much about that. I'm just sort of trying to motivate why we're dealing with the class that we're taking, which is digital control. Meaning we may want to go back and say, can we replace that D of S with a digital device? Can we now substitute, just extract that D of S and replace it with something that we can implement digitally? That's the idea. Can we now replace D of S with a digital device? And that digital device could be a microprocessor, it could be a microcontroller, it could be a computer, it could be a digital signal processing chip. Now our block, we haven't replaced the system. We still have to control the system, which means that we still have this plant, or G of S. We still have its output, which is in continuous time or an analog signal. What we are wanting to do, and hopefully I can fit it all in this dashed area, we now want to replace that D of Z with, let's say, a D sub D of Z. And this is now a transfer function associated with a discrete time system, or you could think of a difference equation. And all of this hopefully will start to make more sense as we get a little bit further into the course. But in order to do that, we still have all of these analog pieces floating around. We still have the analog reference input, let's say R of S. We're still comparing that with the output, which means that this signal coming out of that summing junction is an analog signal, and somehow we need to process that with a sequence of numbers, because that's what d sub d of z wants. It just wants a string of numbers, and it wants to now number crunch on those and spit out another sequence of numbers at a certain time, which means we now want to select or have associated with this dashed block some clock that's driving this process, meaning if this error is an analog, we need to now take that analog signal and make it digital. We now need to go through an A to D converter. Coming out of that d sub d of z block will now be a discrete sequence of numbers. We now need to take that in the opposite direction and go from a digital to an analog signal. We now need to pass that through a D to A converter so that this signal is still, the analog input that's driving our system. The system is still expecting an analog signal. It doesn't know how to respond to 10, then you wait a while, 10.5, and you wait a while. You're just hitting it with numbers. It wouldn't know how to react. You have to give it this continuous waveform so that it would know how to respond. But we could think of different locations here. We now have that point in our loop is now, we could think of it as, in the frequency domain, that's now the z transform of this sequence of numbers. That's now little u of z if coming out of that D to A is little u of s, and coming in is now the frequency domain version of the error signal. And what we will focus on in this class is really a lot of times this transfer function, capital D sub little d of z. What's happening between E of z and U of z? That's what we want to focus on. We want to build that to produce a closed loop system that we are happy with. This, because we are now sampling the error signal, this you could think of or call a sampled data system. And it contains a digital controller. The digital controller is this D sub D of Z block. That's our controller, and that's what we will build in this class. We now want to figure out how do we create or design this D sub D of Z. That's one environment we might have need for a digital controller where the system is actually an analog or continuous time plant or system. We may actually have a generically or inherently discrete time system, and then we also want to be able to control that. Meaning, instead of a capital G of S, which is coming to us from a bunch of differential equations, maybe we have a system that's actually governed by difference equations in the time domain. Meaning we have an inherently discrete time system. Which, if we're in the frequency domain, we would Z transform that sequence of output values coming out of our plant, and that would generate this Y of Z. Then our controller, it's not necessarily the same D sub D as above, but it's some transfer function. But now we no longer have to go converting analog to digital or digital to analog if our plant is already inherently discrete time or digital. We can now simply build a D sub D of Z and interface that where now we have our reference signal, R, in the frequency domain, let's say as little r of z. We can now compare that with this output, and if you were in the time domain, you're now just comparing numbers at particular points in time or at the particular sampling instances, where this now becomes a pure digital system. And we still have the main or same similar components. We still have a system. It's now purely digital. We have a controller. It's now a digital controller, but it's now having to work in this closed loop environment with a purely digital system. Those are these 30,000 feet ideas or concepts that you might want to try to keep in mind as we're working through this class, this material. We are trying to figure out how do we build these discrete time controllers, let's say capital D sub D of Z. In order to do that, we need to get comfortable with systems. Let's now take a little bit of time talking about modeling of systems so that we can become a little bit more comfortable with them. And in this class, we're not going to get too elaborate. We can get as complicated as we want by simply focusing on or concentrating on linear systems. Let's just deal with linear systems. We will concentrate well, maybe I should qualify that. Maybe our systems are nonlinear. We will model them with linear models. Our models that we will be playing with will be linear models. What that means is if we were starting with an analog system or something that is now operating in continuous time, I want you to be comfortable working in different domains, and we will be jumping back and forth between the time domain and the frequency domain, not only with continuous time systems, but with discrete time systems. But for now, let's look at the continuous time. If we were dealing with something in the time domain, now you could think of maybe having some differential equations, or maybe you have your system modeled in a state space representation. Did everyone get state space representation in the prerequisite for this class, which really is ECE 320A at this point? We have to go quite a ways back because 340 is now changed. I like for 340 to be available to you as a prereq just for your maturity level. But in terms of the material in 340A, we probably won't use much of that in this class. But in terms of your maturity, it's good to have. And so a lot of times that is indicated as the prerequisite for this class. It used to be 441A, 541, actually it was 441, was the prereq for this class. We said, let's open it up so that if students forget or can't fit it into their schedule to have the analog class before this, let's not discount them completely from a controls class as they matriculate through the system. Can they now at least get some control class? So now this class is trying to be designed so that you don't have to have already had an analog control class. That's the idea. But we still need to be comfortable with continuous time models. And one of those then could be in the time domain, where if it's differential equations, we might have something like, let's say, y double prime of t plus 4y prime of t, where my prime now means the derivative of y with respect to time. The double prime is the second derivative of y with respect to time, plus, let's say, 13y of t is equal to u of t. And u of t is not the step input. U of t is just a generic u of t. This is now our input to our system. Y of t, let's say, is our output. And now the relationship between the input, if we kick the system, and I'll be kicking things a lot in this class, so I should wear my steel-toed boots, and if you're in the front row, you might wear some shin guards, because you never know what I'm going to kick, but I might excite something. And that should be picked up on the audio, so those people that are listening to this, they know that that was a table that was shaking, right? And they're missing some of this. I hope there's no camera recording this, because we might have some interesting demonstrations. No, we better not go there. But we need to figure out what happens when we excite a system with the input u. How does it behave? Well, this differential equation tells us that. The system is governed by this set of dynamics. We could look at that in the frequency domain as some transfer function, where there's the g of s that we've been having in these block diagrams, which is correlating it with this time domain differential equation. That's now capital Y of s, or the Laplace transform of y of t, the ratio of that with the Laplace transform of the input u of t, which in this case becomes 1 over s squared plus 4s plus 13, and that's now a system description or model associated with that differential equation. But that's now our analog model of a system, and you need to be comfortable being handed that particular description or model in either the time domain or the frequency domain, and we'll then play with that. We also want to be comfortable with these models not only in the continuous time case, but in the discrete time case. Where again we could have these different domains. We might have the time domain, or the frequency domain description, and again in the time domain we might have this in the form of a state space representation. Here in the time domain for a discrete time system, you might be given, or you might be working with, some difference equation. This is now the little n plus 2 sample, the output at that time instant, and I've sort of suppressed the sample period in this argument. And that then might be minus 0.4 y of n plus 1 plus 0.4 y of n is equal to u of n, where again this is now our input. Y of N is our output, and the dynamic behavior of that system is governed by this difference equation. Now, if you have these outputs and inputs as a function of time, they satisfy that difference equation. The output 2 time samples into the future, let's say, is related to the output 1 time sample into the future, and the current output and the current input. Those relationships now govern the dynamic behavior of your system, which now we could say that we could also talk about that in the frequency domain. Now we have G of Z is not the ratio of Laplace terms, but Z transformed expressions. We now have the Z transform of the output divided by the Z transform of the input. We'll deal with this as we go. Now we just are going to see it as a transfer function, which, consistent with this difference equation, this is now Z squared minus 0.4Z plus 0.4. That's our denominator, which means that we have, if we were talking about poles and zeros, hopefully you remember those terms. How many poles do I have in capital G of Z? 2. I have a second order. I now have 2 poles. And we'll learn as we go, but in this class, now we don't have to worry about stability in this infinite expanse of the left half plane, if that's our S-plane. Now in the discrete setting, we get to focus on the unit circle. And we'll learn that the unit circle now, if we can have our closed loop poles inside this unit circle, we will have a stable system. Now, where they are inside that unit circle, we will have to uncover or determine what's the better location. Just like there are better locations in the S-plane for your poles in an analog system. What we need to be able to do, though, is get comfortable going back and forth between all of these different models. Let me just say that. We need to learn how to convert between let's say the different model representations. Now I've already hinted that a prerequisite for this was 320, so I might as well shock us back to reality, and I hope this is a review, but now let's find some equations that govern the dynamic behavior of this system. Let me say this is resistor 1, resistor 2. Those are supposed to be capacitors, capacitor 1 and capacitor 2. And let's say that the output that I'm interested in this particular system or model is the voltage across that second capacitor. And now I want you to write down the equations that govern the dynamics of that circuit. How do you do that? What are you thinking? And just as, maybe I shouldn't do this as a recording, but if you go out those doors to try to find a restroom, you can't get into the Stewart Observatory. That's probably locked since it's after 5 o'clock. there are some restrooms down that hall. If you really need to go, we're not supposed to be in there, obviously, based on the signs. But hopefully I didn't set too many alarms off by doing that. But there are a couple of restrooms just down the hall that way. Where did that come from? I have no clue. Oh, you were getting nervous because I had you try to come up with the equations that govern the dynamics of this circuit. Now, if we're working through this together, how would you do this? And maybe I say, I would like potentially a state space representation for this. How many states are you seeing or thinking there are? All right, now let me see fingers. Not yet, but at the count of 3, I want you to show me fingers. And we'll just assume that the maximum number of states is 5. You can show me no, maybe there's no dynamics. Maybe there's 1 state variable. Maybe there's 2. And so you're showing me the appropriate fingers. Is that clear? And you can show me as many as 5 if you think there are 5 states for this circuit. Okay, at the count of 3, I want you to show me your hand in front of your face, and you can look forward. I'm just curious, how many states are going to be in this model that's governing or describing the dynamic behavior of this circuit? 1. Is everybody ready to answer? Pardon? I want you to answer with a finger. And there is a video recording this, so we want to keep this. No, you guys were the ones that laughed. I just want you to show me a finger or fingers, okay? Give me a certain sign, but be nice, okay? So, is that clear? A set of fingers when I count to 3. 1, 2, 3. Most of you are in a good mood, right? So it is 2, and why did you come up with 2? There's 2 energy storage devices, aren't there? The resistors don't store any energy. You have these 2 capacitors, and those are now our state. We could label the voltages of those capacitors as our state variables. We can now say, if we are writing the equations of motion for this system, we could label this, let's say, as state variable 1, and maybe I'll say there's node 1, consistent with voltage 1, x1, and now we could have node 2 across capacitor 2. And now we should be able to find an equation for x1 dot or x1 prime. I'm going to use those interchangeably. The time rate of change of x1, the voltage across the first capacitor, the time rate of change of x2, we need to write those in terms of x1, x2, and u. Y shouldn't be in our dynamics. Y is our output equation. We should be able to express Y, the voltage across the second capacitor, in terms of x1, x2, and u. That's our output equation. And no derivatives in the output equation. Well, I've sort of given it away in terms of how we might find these dynamics because I've labeled the 2 nodes. You probably, if I had to guess, most of you feel more comfortable writing mesh analysis or doing mesh analysis. So let's write nodal analysis. But nodal analysis is maybe more straightforward for the way that I've defined these state variables, which are these voltages across the capacitors. Let's now write the 2 KCL equations. Associated with this circuit. meaning at node 1, we now could say, well, I have that current leaving node 1, I have that current leaving node 1, and I have that current leaving node 1. If I can write those equations for those currents, those should all sum to 0, since it's a KCL equation. From node 1 going to the left through R1, I want the current. That's just x1 of t minus u of t. I'm assuming u of t was a voltage. That's my source divided by R1. That's the current going from right to left out of node 1. The current going through capacitor C1 in terms of x1, x2, and u, that's just ice, isn't it? Eli the Iceman for ice is now our capacitor. I is equal to C dV dt. This is now C1 x1 prime of t. And then I have the current going to the right out of x1. That's now x1 of t minus x sub 2 of t all over r sub 2. And those three currents leaving that node, node 1, need to sum to 0. That's now one equation that relates the state variables with time rates of change of those state variables. Is it okay where that equation is coming from? You need to get comfortable with that if it's not. But this should be pretty much a review of earlier material. Doing the similar thing for node number 2, now what we want to do is look at the current leaving that node, let's say going to the left, and the current going down vertically from node 2. Those are both exiting node 2. They need to sum to 0. The blue curve going from right to left from node 2 is now x2 minus x1 divided by r2. The current going vertically down through capacitor 2 is just C sub 2 x sub 2 prime. And those two need to sum to 0. Those two coupled equations, they're differential equations, those govern the behavior of that circuit, the dynamic behavior. We now have the time rate of change of x1. That's equal to some linear combination of x1 and x2 and u. We have the time rate of change of x sub 2. That's equal to x1, x2, and u, some linear combination. And then we can write down our output. What is y of t in terms of x1, x2, and u? And that one's really hard. Not, right? Y2, we just labeled that exactly like we labeled x sub 2. Y sub 2 is just x sub 2. So there I've written it in terms of x1, x2, and u. I have 0 x1. I have plus 1 x2 plus 0 u. That's some linear combination of x1, x2, and u. The output equation is simply y of t is equal to x of 2, or the voltage across that second capacitor. That's how we define the output. We now have the equations that govern that circuit. Those are our differential equations, and we have the output equation. And we could write that in terms of, well, those x's and y's and u's to get a state space representation. With a little algebra, I will let you do that at home. You can go home and do that and check my work, but that algebra now really will give us a state space representation. Meaning, if we go back to this node 1 equation, isolate x1 prime on the left and put everything else on the right of that equality, divide both sides through by c sub 1, we will now have an x1 prime equation. If we do that algebra, hopefully we will obtain x1 prime of t is now equal to minus 1 over r1 plus 1 over r sub 2, 1 over c1 x sub 1 of t, plus 1 over r sub 2 c sub 1 x sub 2 of t, plus 1 over r sub 1 c sub 1 u of t. And that's now our x1 prime equation in terms of x1, x2, and u. But that was obtained from that node 1 KCL equation just by solving for x1 prime. x2 prime, doing the same, is now 1 over r sub 2 c sub 2 x1 of t minus 1 over r sub 2 c sub 2 x sub 2 of t. And y of t is just x sub 2. We can now put this into a block diagram. We can put this collection of coupled differential equations into a block diagram. Let's start with the time domain, since we are dealing with differential equations which are in the time domain, and this will be called our all integrator block diagram. Do you remember how we create block diagrams? And if you don't, then this might be a little bit more background review for you to do. But to put these two equations into an all-integrator block diagram, how many integrators am I going to need to essentially solve these two coupled differential equations? 2. Right? I have an x1 prime, I need to integrate that. I have an x2 prime, I need to integrate that. Those now, x1 and x2, will be the outputs of these two integrators. I now need to, in this block diagram, produce x1 prime with summing junctions and gain blocks. I need to produce an x2 prime, and then I will have my block diagram realization. And that, in fact, would be an analog computer. If we went old school, we would now have an analog computer that consists of integrators, gain blocks, and summing junctions. And you could then simulate this system that might be a 757. You now have it as a differential equation. You can now build it on a breadboard and simulate it. Maybe it's a scaled version, but now you could inject some input signal and solve those differential equations with an RLC op-amp based circuit by building up this all integrator block diagram. Doing that, what I am trying to say is we now have two integrators. If I can put all of this on this page, there are my two integrators. Let me go ahead and say that the input to this leftmost integrator will be such that the output is x1, meaning the input must be x1 prime. If we do the same for the rightmost integrator, this is now x sub 2 of t. The input to that then must be x2 prime. And we have equations for x1 prime and x2 prime sitting right there. Meaning x1 prime is some scaled version of x sub 1 plus some scaled version of x sub 2 plus some scaled version of u. We are scaling u by 1 over r1 c1. There's now u of t pushing through a scaling of 1 over r1 c1 and making up a piece of x1 prime. x1 prime is also made up of some combination of x1 let me pull that now down here. That's now taking x1, scaling it to produce one of the other pieces of x1 prime. And the last piece of x1 prime is a scaled version of x sub 2, which is scaled by 1 over r2 c1. I'll take x sub 2 scale it by 1 over r sub 2 c1, and now I've built up the expression for x1 prime. x1 prime is coming out of the summing junction. That needs to equal everything that's going into it. And that was what the first equation allowed us to do, or gave us that relationship. To build up x sub 2 prime, it was made up of a scaled version of x1, which is r2 c2, and a scaling of x sub 2, which is minus 1 over r2 c2. We now have a block diagram description, and this is actually, since y of t was just x of t, now if somebody built this all-integrator block diagram in the lab with op-amps, resistors, and capacitors with these gain values and these summing junctions, you could simulate that circuit. Or you could build the circuit and drive it and see what you're getting for y. But now you have a different way of thinking about that electric circuit. You could build this in a block diagram in MATLAB. And now you don't have to go into the lab. You can now put this into your computer and inject different types of voltages for u of t and see what happens at the output y of t from that RC circuit that we started with. This is in the time domain. We could look at that in the frequency domain as a block diagram. And to do that, why don't I just collapse? I'm getting tired of writing all these R's and C's, and who knows, I may have gotten some subscripts wrong. You can go back and check me. But let's call this gain block beta. Let's call this one alpha 1, 1. This one alpha 1, 2. This one alpha 2, 1. And this one alpha 2, 2. So that now in the frequency domain, if I simply created a block diagram in the frequency domain, I'm going to have those same gain blocks. My integrators now will be replaced with some other expression. What's an integrator as an operator look like in the frequency domain? 1 over S. So now all of my integrator blocks are replaced with 1 over S operations in the frequency domain. Everything else looks exactly the same as my time domain block diagram. I now have these summing junctions. I have my alpha 2, 1. I have my alpha 2, 2. And those now combine to give me the Laplace transformed x sub 2 of t, which is now capital X sub 2 of s in the frequency domain block diagram. I don't have x dots anywhere. This is now in the frequency domain. I also can now pull off x sub 1 of s, scale that with alpha sub 1, 1. I can scale my u of s with beta, and I can now take x sub 2, scale it with alpha sub 1, 2, which is really just that RC coefficient or combination. I just tried to minimize the number of expressions in the blocks, and this is now my frequency domain block diagram. And you should be comfortable dealing with all of these. Somebody gives you a time domain all integrator block diagram, maybe they give you a frequency domain block diagram that looks like the one on the board. If we go back here to the time domain and use the same coefficients, you should now be able to immediately write down the state space representation for this block, from this block diagram. Meaning, now we could look at this and say, oh, from that earlier all integrator block diagram, I can now build up a state space representation. And what's critical here are how tall my state vector is, how tall my input vector is, and how tall my output vector is. And then all the different matrices that relate those vectors. How many state variables did I have? 2. I had an x1 and an x2. The state space representation says you need to find or rewrite those equations to isolate x1 prime, x2 prime, x3 prime, etc. in the left-hand column. We go back to our all integrator block diagram and we see that x1 prime is simply alpha 1, 1 x1 plus alpha 1, 2 x2. And that now tells us the coefficients in our system matrix that scales or weights the state vector x1 of t, x2 of t. To complete the top row of this expression, I now need to introduce the input. Our input vector is a big vector. It's a scalar. It's a 1 by 1. It's just one input. That's u of t. And it now, for x1 prime, was related to part of x1 prime by scaling the input u with this parameter beta, or 1 over r1c1. Meaning in our input matrix B, there's now beta. We can do the same process for filling in the entries in our matrices to create x sub 2 prime. x2 prime is just alpha 2, 1 times x1. It's alpha sub 2, 2 times x sub 2 plus how much? U. There is no U directly feeding into that summing junction, is there? It will, U will excite x sub 2, U of t, not YOU, but U of t will excite x sub 2, but it's indirectly. It has to be processed through these feedback paths in that integrator, but going directly into that summing junction, there is not a gain value directly from U, meaning there's nothing that's going from here through some gain up to here. This is now that 0. It didn't exist, which means that in our input matrix, that's a 0. The other pieces are now alpha 2, 1 and alpha 2, 2, which weight x sub 1 and x sub 2 respectively. This is what we will call our system matrix, or the A matrix. And we can actually have a continuous time system matrix and a discrete time. We will have state space representations for a discrete time system. Also, in addition to having to deal with continuous time state space representations, today we're focusing on differential equations and time domain. This matrix is our B matrix. We could call that, or will call that, our input matrix. The output equation is some linear combination of our state vector plus some linear combination of our input. Now we need to fill in those entries in those matrices. This matrix that weights our state vector typically might be labeled with a capital C, and this is our output matrix. And this matrix, which is a big matrix, it's relating a 1 by 1 U with a 1 by 1 Y. It's a 1 by 1 D. That's why I said it was big. It's a scalar, but this is now our direct feed through. Matrix. There was no direct connection between the input U and the output Y. There's no path there, so that was 0 in the output equation. And what did make up Y of t? Y of t was only made up of x sub 2 of t. To make that happen, our output matrix C is just 0, 1 as a row vector. Now, we are going through all sorts of relationships. Why don't we now jump back into the frequency domain? This is a time domain, state space representation of that RC circuit, a second order circuit. We could also find the transfer function either by analyzing this circuit directly in the S domain, which is what you would want to do. I know that's just how we want to do it as electrical engineering majors. We want to put this into an S domain equivalent and solve this. Then we could look for the transfer function between U of S and Y of S. But now that we've gone through all these different versions or representations of this system, why don't we find the transfer function algebraically from these matrices A, B, C, and D, so that if somebody now gave you a different system, but it was in terms of A, B, C, and D, you could plug those A, B, C, and D into this expression and obtain the transfer function. Your A could be 10 by 10, which might happen on the first exam. You might have a 10th order system. You might have 3 inputs. You might have 2 outputs. Just saying. But if we now looked at the transfer function here, if we find that algebraically, we could actually find it from this block diagram, couldn't we? This is actually just y of s. We could do Mason's gain. Did you have Mason's gain in 320? Probably not, huh? Or you could do block diagram algebra and find the relationship between u of s and y of s in this block diagram. Or you can Laplace transform this state space representation and solve for the relationship between u of s and y of s. Meaning now we have, let me just say we could find this transfer function from the block diagram. But we'll leave that for another time. We now have this x dot is equal to a x of t plus b u of t. Y of t is equal to c x of t plus d u of t. We now have, let's say, this state space representation. If we Laplace transform that, what do we end up with? Do you remember what happens when you Laplace transform a derivative? You multiply by s, don't you? But now that little x of t is a vector. It's stacked up. It's a bunch of different time domain variables. It's an x1 and an x2. It's a voltage on the first capacitor and a voltage on the second capacitor. So I might have a stacked vector scaled by this frequency variable s. If I Laplace transform this, I now have s, x of s, minus the initial condition vector, x of 0 minus. That's what happens when you Laplace transform a derivative. You have s times the Laplace transform of the variable. Now we have all these variables in the state vector, minus all the initial conditions. That x of 0 minus represents this tall, thin vector x sub 1 of 0 minus, stacked on top of x sub 2 of 0 minus, stacked on top of x sub 3 if it existed. Then we would have this is equal to a x of s plus b u of s. If we're interested in the transfer function, then we wouldn't worry about the initial condition. And we would insert a placeholder, an identity matrix. I'm going through this pretty quick because we're almost up to 9 o'clock. Not quite. But this now becomes si minus a times x of s is equal to b u of s The output equation is now y of s is equal to cx of s plus d u of s. If we solve this for capital X of s, and now put this x of s in for that, we then end up with y of s equaling c times si minus a inverse b u of s plus d u of s. We can factor out that common variable u on the right-hand side. And we now have gone back to this transfer function g of s in terms of our state space matrices, capital A, B, C, and D. You've seen all sorts of different models tonight. You've got a week to digest those. We'll pick up at that point a week from tonight. Enjoy your 3-day weekend, and we'll see you next week.